All right, kids, let's get going here. Yep. Well, hopefully we'll be back. Okay. So you had that math problem, and I know that once you saw that first derivative was a quotient, you probably just gave up. But I'll see if anybody was tough enough to get the second derivative. You did try? Okay. All right. Well, I'll be the judge of that. And guys, this is what I want you to do while waiting. First of all, notice there are two piles on your desk. One side, you have a take-home quiz. It's due on Wednesday. It does not say it on it, so you need to write on it due Wednesday. Very exciting. Now, underneath it is just a nice flow chart kind of summarizing how to graph. You know, that's just there for your own enjoyment. So that's the take-home quiz, and we're going to practice that again today, doing problems like that. Then the other thing you have is today's notes, and today we're going to go through one of these, sketching a complete graph of a function, and we're going to do it for a rational function. Bless you. So that way you'll be all set for your take-home quiz. Yeah. W-E-D-N-E-S, Wednesday. W-E-D-N-E-S-D-A-Y. Did I misspell something? Oh, no. Oh. Just a W-D. Jillian, ask the English teacher. Oh. Should have got Mr. Pereira in here. All right, we are in calculus class, believe it or not. All right, we kind of went off on an English tangent. All right, guys, we're on the air. We're recording. All right, so. I know. All right, what I want to do, when I'm checking your homework, what I want you to do is fill in this information. I've given you all clues, but before you do that, I want you to factor, rewrite the function, clean it up a little, and then you can tell me what the domain is. And I give you the hints underneath. You know, just don't let all reals such that the denominator doesn't equal 0. Find the x-intercept, set y equal to 0, and solve for x. A fraction equals 0 when the numerator is 0, etc. So go through, fill in this information, and then we'll get the first and second derivatives, and we'll put it all together. Okay, so we're back. All right. Guys, when you factor the numerator, can you tell me what you get? 3 x, what was it? X minus 4, and then what was the other one? X plus 2, okay, and the denominator? X minus 2 squared. Now that's going to help us answer these questions, because the first thing I ask you for is the domain. Domain, you got to make sure that you don't divide by 0. So what's the only value that x cannot equal? Or just, how about, all right, so yeah, x can equal 2. So x can be any value from negative infinity up to 2, and then from 2 to positive infinity. If you wrote x is not equal to, that's okay. I'm trying to get better with the interval notation. Okay? Does everyone see where that came from? Yes. It's a little awkward, but, you know, you could do all reals, and then you could say, you know, such all reals. You could say such that x does not equal. To use interval notation and then say on the side something is a little awkward. I know what you're saying, but I want you to be able to get your ideas across well. Yeah. Okay, x-intercepts. That's values of x that make y 0. And y is a fraction. A fraction equals 0 when the numerator is 0. So what values of x make y 0? X is 4 and negative 2, right? You guys see that if x is either 4 or negative 2, y will be 0. So our x-intercepts, we're going to write them as points. We have -2, 0, and 4, 0. Those are the 2 points on the x-axis, on our graph that are on the x-axis. Now for y-intercepts, that's when the x-coordinate's 0. So if you put in 0 for all these x's, what do you get for y? So if x is 0, yes, Karen, -6. Anyone else getting -6? Yeah? Nice. See, we're getting some actual points. We've already got the intercepts. Those are points on the graph we're going to be able to work with. Now, vertical asymptotes, if you recall, occur at any value of x that makes just the denominator 0. So are there any values of x where the denominator is 0 and the numerator is not 0? 2, right? So x equals 2 is a vertical asymptote. So we're going to write our intercepts as points, and our asymptotes we write as lines. We have to, write x equals y equals. Now, horizontal asymptote, I don't know if you remember, you take the limit as x approaches plus or minus infinity. And if you take the limit as x approaches plus or minus infinity, do you remember those cases? Yes. The degree's the same. Yeah, divide what? The leading coefficients. So it's the ratio of the leading coefficients. So the limit as x approaches positive or negative infinity is going to equal 3. So the equation of the horizontal asymptote, very nice. We are zipping along. Now, that's all the information we can get without getting into derivatives. Now we got to get into some derivatives here. So we're going to take the first derivative. I do suggest that we keep the denominator as x minus 2 squared. I don't think keeping the numerator written as a product is going to be very helpful. So I think I'm going to leave the numerator as 3x squared minus 6x minus 24. We'll get the same answer. I'm just trying to minimize the pain. So the x minus 2 squared, it's nice. So we're going to have to use the quotient rule, right? So we have, what do we have here? 3x squared minus 6x. And what was the last term? So we're going after the first derivative, which will help us see where we have any max or min values, right? Quotient rule. Now, I suggest you guys write small. Well, it's going to take a little bit. It's not, I mean, I gave you some room, but I don't know. Some kids were complaining. Okay. Low D high. So low is no problem, right? X minus 2 squared. What should I write for D high? Minus 6. Good. Less high. Well, we got that whole 3x squared minus 6x minus 24. What about for D low? Chain, chain, chain. So 2 times x. Nice. And that's it, because it's to the first, root of the inside is 1. I'm not forgetting the chain rule, right? If I write a little 1 here. All over. Now, the denominator squared is x minus 2 to the 4th. Nice. Now, before you can get critical values, you got to clean this up. First, you look to see if you can factor anything out. Then you're going to have to distribute and combine like terms. And you want to clean things up. You can't just look at that and say, I don't know where that's 0. I give up. Can't be like that, right? All right, so what can we pull out here? An x minus 2. You all agree? Of course we do. You can put a red set of parentheses. No, I'm connected. Sorry. Okay, we're back. So where were we? We're factoring out the x minus 2. So what goes in here? Okay, so we have the x minus 2. 6x minus 6. And then over in that second term, yes, minus 2 times 3x squared, that thing, 6x minus 24. This is all over the denominator. Goes to the, okay. Now I need to get this thing out of here. sorry, kids. Yeah, we could cancel. You know, whenever you cancel a factor that has an x in it, just be careful. You know, like say to yourself, oh, well, what if it equals 0? I'm dividing by 0. That's illegal. But we know that x can equal 2 because that's not in the domain, right? So it's okay if you want to cancel that. I'll do that. Sure, I'll play along. Okay, now, still, this is not the best derivative. Now we still have to distribute and combine like terms. We tried the GCF and whatever we can out of there, so that sounded wrong. All right, so it did. I don't know. Sorry about that. All right, so if we distribute over here, I'm going to distribute the x and then the minus 2. You can distribute in whatever order you'd like. So 6x squared minus 6x minus 12x plus 12. So I distributed the x first, and then the minus 2. The order doesn't matter. Distribute. Then we'll distribute the negative 2, and we have minus 6x squared plus 12x plus 48. Oh, x minus 2 cubed now. So, you know, we have to distribute, and we gotta combine like terms. We gotta clean it up more. Does anyone see anything that will the 6x squared, the minus 6x squared? Gorgeous. 12x and oh, nice. All right, so that numerator, let's write what's left in the numerator. We got negative 6x, and what's the constant? 12 and 48. What does that add up to? 60? Oh, this is nice. So here is our cleaned up version of the first derivative. Critical values occur where the derivative equals 0 or is undefined. So for our critical values, what value of x will make it equal 0? 10, right? A fraction is 0 when the numerator is 0. So when you set that numerator equal to 0, you get x equals 10. So that's a critical value. But we also have critical values when it's undefined, when the denominator equals 0. And that happens when x equals 2. So we have two critical values. So we're going to make a sign chart. We're going to mark it at 2 and 10. So here's my first derivative. I'm going to move down my critical values. Making a sign chart, marking off at 2 and 10. Yes. Sure. What about that 2? Uh-huh. Yeah, well, if it was just on that, if it was a factor, there was also something about, we saw 2 before. When did we see 2 before? When we started this problem. Do you remember that? There was a vertical asymptote there, and so was 2 in the domain? No, and something to keep in mind, you're right, it could, so it's, 2 is not even in the domain. So you want to be very careful that, you know, just to never say you've got a max, a min, a point of inflection at an x value that's not in the domain. So we're just keeping that in mind. I wrote that underneath the domain part. Okay, so let's take a number greater than 10. I want to start all the way over there. All right, I'll go with the 11, fine. If x is 11, is the numerator positive or negative? And what about the denominator? So you have a negative over a positive. Nice. Give me a nice number between 2 and 10. And then you pick what you want. I'm going with 5. It's a little easier for me. If x is 5 or any number in here, is the numerator positive or negative? Positive, right? Like negative 30 is positive. And what about the denominator? Positive, so the quotient is... Ooh. Okay, let's take a number less than 2. 0. Okay. If x is 0, is the numerator positive or negative? And what about the denominator? And a positive over negative All right, we got a sign chart. Now, you see how it says relative min? Normally, you would yell out what? A 2, right? But what's the reason we can't write there's a min a 2? Yeah, it's not in the domain. So we're not going to have a min. All right, so just even though there's a sign change, there's no min. Because, you know, you can only have max min or a point of inflection at a point that's actually on the graph. You can't say, oh, the min would be there if it was there. But no, it's not. It's not there. All right, and max, where's the max? At x equals 10. Yeah, what is the y? Why might as well figure it out? We got to go back to the original. You got to plug 10 into the original for making us go get that. Well, we're going to have to get it anyway. Might as well get it now. Everyone's waiting for someone else to do it, right? I'm trying to remember what the factors were. So it was x minus 2 squared, 3 times x. So if x is 10, 3 times 6. What? Don't even tell me we're going to have a fraction. What is the reduced form? Because I haven't. What is it? I don't feel like it was 1/4. 27 over 8? Yeah, because I had, that would make sense. All right. 27 over 8. Can you give me, like, that's in between what two integers? Almost 3.5. Great. Great. Okay, well, that's an important point along with our intercepts, but we have to go for the point of inflection because that could be an important point too. So let's get the second derivative. We're going to use the first derivative as negative 6x plus 60. Let me get to the next page. And then we have x minus 2 cubed. All right. So now we're going to use the quotient rule again to get the second derivative. So low. We're starting this out. Second derivative equals x minus 2 cubed. What's the high? Negative 6 less high 6x plus 60 below 3 times x minus 2 squared, because the derivative inside is just 1, so we don't have to write that. All over x minus 2 to the 6. Good. Okay, now, again, because you want to find out where it's 0 undefined, you got to clean that numerator up. Yes? That's a great idea. And I'm going to rewrite this negative 6x plus 10 as negative 6 times x minus 10. All right, yeah, we're going to factor out. That was he got the right GCF to pull out. So it's a negative 6 times x minus 2 squared. Okay, now, that's the common factor. So how many times does that go into the first term? What should I write here? What's the first term going to be, or rather, just an x minus 2? Now, think about what we're pulling out. We're pulling out a negative 6 x minus 2 squared. So what we're pulling out is the negative 6 and the x minus 2 squared, right? Now, so what's going to be left? X minus 10. And we have a minus out there, so we have a minus 3 times x minus 10. Is there questions on that? Factoring that negative 6x minus 2 squared out? Well, Cameron saw that because he saw that it was a factor of this term also. You know, you see the negative 6 here, but if you had further factored this, like I did right above it, then you would have seen it, right? Yeah, you'd get the same thing in the end. You'd have just had more combining to do. You're going to get the exact same answer. It's just that the more you can pull out, the less you have to combine. So, but it's all going to work out the same. All right, so we're cleaning up the second derivative. So we have negative 6 times x minus 2 squared. When I clean up this x minus 2 minus 3 times that, how many x's are we going to have in there? We combine the x's. Negative 2x. Now, if we multiplied and then added, as PEMDAS tells us to do, plus 28. What x minus, oh, these? Yeah, I can next. I'll do that. This was looking on cleaning up that other factor there. So you pull out where you can the GCF, and then you clean up what's left. Because you got to be able to see when a fraction is 0 undefined. And now it's going to be easy. And as you just said, we don't have to worry about x, you know, that we're dividing by 0. We know x can't equal 2. So I am going to cancel that. And now what's the new exponent going to be on the x minus 2 in the denominator? 4. Okay. So this is good enough. We're going to be able to get what we need now. Let's find out where our second derivative is 0 and where it's undefined. So if I want to find out where the second derivative equals 0, we set the numerator equal to 0. What value of x is going to make the numerator equal to 0? X is 14. Okay. What value of x will the second derivative not exist? So those are the only values where the second derivative could change sign. So we're going to make our little second derivative sign chart. It's going to be adorable. We're going to mark it off at 2 and 14. Now, we're going to take a value greater than 14. I mean, if you do you guys want me to pull something else out of here, or can we just work with it as is? It's up to you. We can deal with it, right? All right, give me a number greater than 14. All right, 20. All right, so if x is 20, I know negative 6 is negative. What about negative 2x plus 28? So that's a negative times a negative, so the numerator is positive. And you know what the great thing is, guys? X minus 2 to the 4th is always positive. So once we figure out the sign of the numerator, we're good. So what do we say was positive over here? What about a number between 2 and 14? 10. I'm taking 10. Sorry, I'm taking 10. Negative 6 is negative. If x is 10, negative 2x plus 28 is positive. And negative times a positive, negative. Now I need a number less than 2, 0. Sorry, I was looking for 0. All right, negative 6 is negative. If x is 0, that's positive. So a negative times a positive is negative. Okay, do we have any points of inflection? At 14, you know what I'm going to ask you to do? The y value. You got to plug 14. Yeah, didn't I have room for the second derivative on the back? Very good. Very good. The original. Anytime you want to get a point on the graph of f, you have to plug it into f. I feel like it comes out to be 10/3, but I'm not sure, so I'm going to wait for, I need one of you guys to tell me, because I know it was 3 point something. Maybe it was not 10/3. Yeah, plug 14 into the original function for me. Yeah. You got 10 over 3? Okay, good. That's what I thought it was. That's what it is. Nice. Okay. What's that? Where? What? Oh, I don't know if I can help you with that. You know how long you were gone for? Were you gone for like 5 minutes, 10 minutes? Oh. 14 when we set the numerator equal to 0. When we cleaned up, when we pulled out the GCF, what was left was x minus 2 out of the first term and a minus 3 times x minus 10 out of the second term. And we distributed and combined like terms. Well. All right, let's put this together. This is so exciting, it's overwhelming. All right, 214. Now, I'm going to put the little sign charts down here. Okay, so from the second derivative, I know it was 2 and 14. 6, 8, 10, 12, 14. The original. You always go to the original. Always. Keep saying that. Hey. Okay, so 2. And the first derivative sign chart, can you remind me how that went? And what were the values? 2 and 10. Okay. Wait. Oh, I didn't line that up. 10's over here. Okay. Okay, you said it was negative, positive, negative? Now, this is so exciting because we get to fill in all these points. Let's get this out of here. Okay, the x-intercepts, that was at negative 2, 0, and 4, 0. Negative 2, 0, and 4, 0. So negative 2, each box on the x-axis I had to make 2. Negative 2, 0, and 4, 0. There's 2 points on a graph. Very exciting. The y-intercept, we got 0, negative 6. 1, 2, 3, 4, 5, 6. Negative 6. There's a point. Vertical asymptote, that was x equals 2. A nice green vertical asymptote for us. And a horizontal asymptote, we have y equals 3. I'll make that in green also. 1, 2, 3. Those are little guidelines for our graph. Relative max. There was no max?
No, 27 over 8.
Oh, there was. Okay, 10, comma, 27 over 8. So when I go to plot that point, I'm going to go a little, like Cameron said, it's a little less than 3.5. So 10, 1, 2, 3, so like right here. That's going to be a max. Now min, there was none, right?
No.
Point of inflection, that was at 14 10/3. Now 10/3 is 3 1/3. It's very, very close. I'm going to try to make theirs show a difference. 10/3. That's about as good as I can do. Now, connecting them all with the right kind of curves is the fun part. So all the way up to 2, I know I have to draw a curve where the first and second derivative are both negative. So it's decreasing and concave down. So we're going to go through the points we've got. Okay, so it's, oh man, I'm doing it backwards. I don't know why, but whoa. But I missed my y-intercept. Yeah, there we go. Oh, perfect. Oh, no. All right, well, that's good. I'll just make the point bigger. I got it. Okay, now, between 2 and 10, first derivative is positive, second derivative is negative. Increasing concave down until 10. So, this is going to be a max here. I'm drawing it backwards, which might be confusing for you kids. I don't know, I shouldn't have done that. But yeah, it's increasing concave down. Yeah, they can. I told you in the beginning, you only, a graph cannot cross a vertical asymptote, but it can cross a horizontal or slant or any other. Okay, now, between 10 and 14, what's the graph got to do? Decreasing and concave down. So this is hard to do because we have such a little space, but it's decreasing concave down. The max should have been over here. Oh, I'm sorry, I'm keeping it. No, I shouldn't. Yeah, oh, thanks. All right, decreasing concave down. And then when it gets to that 14, it's still going to keep decreasing, but what happens to the concavity? Concave up, so it just like concave down, like goes that way. So the concavity changes there. How cool is that? Yeah. So like this, I mean, I didn't do the best job because I missed that right there. And if you look on your calculator, not that I'm saying, but you want to verify this stuff, this is what you would see, It looks flat here on the calculator. They don't really show the max and the concavity changing. That's what we've got to get from your calculus. Now, guys, if I were you, please look over the solutions that I provided for the last night's homework so you can see where it was you went wrong. And when you do the homework, of course, that the take-home quiz is due Wednesday, but of course you're going to want to check with the calculator. Bless you. It's a take-home quiz, okay? But do all of your work analytically. Fine to use the calculator to see if you're right. Yes. The test is not like the quiz. I do have the review sheet for the test if anyone wants it early. I was going to give it to you tomorrow. Yeah. If anyone else. So this week, extra help is Wednesday. The test is Thursday. All right.